Yeah, hi everyone. I'm going to quickly go through some theory and applications of exponential functions. First thing, you should have already know a lot about polynomial functions like x squared and x cubed and x to the power 4, those sort of things, where x is the base and a is the exponent. Well, exponential functions, when you flip around, when you've got your constant is in your base and your variable is in the exponent. That's why they're called exponential functions, because the variable's in the exponent. Now, you'll find this a lot when we're talking about growth and decay, or when you're talking about compounding interest and depreciation. So lots of financial, but also biological and ecological applications. Also in material science and engineering as well. Okay, so we're going to define an exponential function as y equals a to the power x for now. A has to be a positive number. If it's negative, it'll keep switching, and you'll get undefined answers all the time. You can investigate that yourself a bit more, why that's not possible. And a does not equal 1 because 1 to the power x is always equal to 1, so you'll have a horizontal line. And y equals 1 if a equals 1. So it's got to be greater than 0 because negative numbers are not possible. 1 is possible, but it's not an exponential function, it's a linear function. Okay, so we're going to investigate properties that have this format. So you can multiply a constant at the front, you can multiply x by a constant, and you can add a plus c at the end constant. We're going to see how those three things affect the graph. First of all, there's y equals 2 to the power x. Most important thing goes through 0, 1, because 2 to the power 0 equals 1. Has an asymptote, which means it approaches the x-axis but never crosses it, so the x-axis is the asymptote, and it grows very quickly when x increases. Okay, so that's an exponential graph of y equals 2 to the x. We'll just keep that there and look at 3 to the x. So you can look at the differences now. Well, similarity, they both go through 0, 1, because 3 to the power 0 equals 1, just like 2 to the power 0 did. But you can see it gets closer, on this side it gets closer to the y-axis, and on this side it gets closer to the x-axis. Okay, and how about 5 to the power x? It's getting closer to the axes as well, still going through 0, 1. So, the higher the base, the steeper the graph, the quicker the growth, and all three go through 0, 1. If you put a negative out the front, it obviously, as you've seen here, reflects it in the x-axis. Now, if you do a half to the power x, or anything less than 1 to the power x, that's going to be a fraction. When you got fractions, or when you got a 1 over, you've got a negative power. A half is 2 to the negative 1. So a half to the power x is 2 to the negative x. So then that negative is going to reflect it in the y-axis. So if you're increasing, you got 2 to the power x with a positive x. If you're a decreasing function, or if it's decay rather than growth, you'll have the power of negative. You have 2 to the power negative x. The power will be negative. Okay. It still goes through 0, 1 though. Okay, if you put a plus 3 on it, let's just shift everything up, and you would have seen that with straight lines, with quadratics, with other polynomials as well, with trigonometric functions. You put a plus c on the end, it'll just move it every point up by c, including the asymptote and the intercepts. So now the intercept is at 0, 4 because you've moved it up. The asymptote is not the x-axis anymore, it's y equals 3. Okay, if you multiply by 3, multiply by a constant at the front, it's going to vertically stretch your graph, which means it'll change the intercept, but not the asymptote. Okay, so you can think about that and try and make your own examples and see how the pattern emerges there. Okay, if you multiply the x, that will also make it grow faster. So you've got, this time we call this a horizontal stretch, but it'll still go through the point 0, 1. Why? Because 3 times 0 is 0. The other thing you've got to notice is 2 to the 3x is 2 to the power 3 to the x. So this is 8 to the power x. So you can use the same rules as you did before. And for those of you who know about the number e, this is how you can transform also into the number e. So that's a little summary of how all the different factors work. So just like any other function, that's your vertical stretch, the k at the front. The lambda here is your horizontal stretch or compression, and the plus c moves it up and down. So here's a challenge. Find the equation of the red curve. Well, we know it's been transformed from 2 to the power x. You have to work out what k is and what c is. Okay, well, we can do the c pretty easily. It's been moved down from there down to there. So the c is going to be -5. But instead of going through 0, 1, if you moved it down 5, it would go through 0, 4. -4, sorry. But now it's going through 0, -2. So it's been stretched. It's been stretched by a factor of 3. Now you can find out that stretch by substituting in some points and see what happens. If you can't see that automatically, that's 3 times what it should be, or what it was. Okay, let's go on to some applications. We've already talked about what they could be. Here's a couple of actual applications. So, a city in Germany, Dresden, has a population of that, and the 2 would suggest it doubles, and it doubles every that many years. So when whatever years would make that a 1, that's how long it would double, how long it would take to double. So if in 2000 the population is, well, is that, because you put in 0, and that would be 1. So in 2000 the population is 500,648. In 2008 you put an 8 in there, and you get 535,096. When will the population be over 700,000? Well, you put in 700,000 for P, and you work it out. Now, if you know how to do logs, do it. Otherwise, you can plot it on a graph, or as well, you can plot it on a graph. And then you put a line across at 700,000 and put it down to the years, and it should be 2041 when the population becomes 700,000. You can check my answer using logs if you want. Now, notice this doesn't quite look like a curve. It looks pretty straight, but actually it is a curve, but because this number is so low, it's not quite as happening. The exponential growth is not quite as distinctive as in my examples before. And also I'm just taking a small section of the graph, so it looks kind of straight, but it's not, it's curved. Okay, and yeah, right. It's always a good plan to check your answers. You have a calculator, use it. Second example, okay, I'm doing compound interest. I have $4,000, I get 6% compounded annually. So my formula is 4,000 times 1.06 to the n, and its number of years. Okay, we'll do it graphically. There it is. That's what it looks like. What would be the final value in 10 years? Well, I go up from 10 and go across, and I can work out 7,163. Okay, you don't have to use a graph to do that. Just put it in the formula. How long should I invest in order to earn $6,000? Well, you can use the graph for that since you've already drawn it. Just go across from 6,000 and down. Looks like 7 years. You probably want 7 whole years, but using logs or using the calculator solver, you can get 6.95 or 6.96 years. Okay, last example. We've got a pot of water on the stove. Temperature is given by that formula there. When T minutes have to take it off the stove, obviously it will cool down when it's not on the stove. So draw a graph. There's our graph. Okay. And you can see it's exponential, sorry, because it has that curve shape, but it also has the asymptote over here. That's important for the rest of the question. Okay, what is the temp when it's removed from the stove? Well, when time equals 0, put that in the formula, you get 100 degrees. There it is. Okay, so it was boiling. What's it after 10 minutes? Well, put 10 in the formula, and you get 46.6. Just to check it, you draw a line across and a line down, and they do meet up at 10. Bit inaccurate there, but you get the point. Okay. When will the temp be 40 degrees? When you go across from 40, go down, or use logs. You put it in. I put 40 in for the capital T here and use logs to work it out, or use your equation solver. You get 12.5 minutes. What will the minimum temp be? Well, because our asymptote here is 18, when t equals infinity, this will be 0, so you get 18. So it'll approach but never equal 18. So minimum temp would be just above 18. Alright, well I hope that little explanation of those illustrations help you understand how to do exponential functions. And yeah, onwards and upwards to infinity and beyond with your